All right, field theory. These are the gravity ones. These have to do with mass. Okay. The first one is Newton's theory of universal gravitation, right? So this is G. This is our 6.67 times 10 to the minus 11th. That's in the front. This is one mass. That's another mass. This is the distance separating their centers. So if you've got two masses here, right? R has to be not the center to surface distance or surface to surface distance, but literally this distance from the center to the center. And if they're spheres, by the way, it works out exact. And then if it's, some other shape, like a rod and a point mass, you'll do these in calculus in college if you haven't already done them. Okay. But anyway, there it is. And this force is, of course, in newtons, right? And then this is what Newton meters squared per kilogram squared, right? So basically, when you plug those units in there, you end up with newtons, right? Anyway, so that is the force of gravity between these, right? Now we're talking about field, right? So field is sort of in the subjunctive sense. Like if we did have a mass there in this field, it would experience a force of this, right? So for example, near the surface of the Earth, G is 9.8 newtons per kilogram. If I have 1 kilogram of mass, I'll have 9.8 newtons. If I've got 100 grams, I'll have 0.98 newtons or something like that, right? Okay. So that's what this is, right? So this is the force of gravity is mg, right? Okay. This is, if you look at this is all we've done here is we've divided this force equation by a mass, and we end up with this. So this is, if I have a mass here and I'm some distance from it, right? From the center, this distance has to be from the center, right? My gravitational field at that point is G big M over R squared, okay? So notice that the field equations have R squared in them. This is important. The vectors have R squared, okay? These things are scalars here. This is energy per unit mass, et cetera, right? Okay? Those things have just an R in them, and that's one way you can tell the difference, okay? Now we're looking at potential, right? So this is literally an energy here, okay? So all this is this is this is potential energy, right? This is potential. Notice that it's just this equation down here multiplied by a mass, okay? So now if we look at this guy, the potential energy is, if I have two masses, right, and I bring one mass in from infinity, right? If I bring this guy in, here's infinity, right? Or very far away, right? I'll say that, right? And I bring it to some position where it's r distance away. This is how much energy you have. And of course, notice it's negative, okay? Because of course, it's really the energy you would have to move this other mass or both masses, or it doesn't matter, right? So that they're infinitely far away. Okay, so the gravitational potentials are all negative. Okay, and when you look at the universe as a whole, right? The universe was created by the Big Bang, and one of the conundrums of it is that the matter in the universe represents a tremendous amount of stored energy. So does that mean that the Big Bang in the creation of the universe violated conservation of energy? But it's quite possible that all of the negative gravitational potential, because all of that energy is negative, counteracts the positive energy represented by mass. Well, you just didn't need to know that, did you, for the IB test? Okay. Sorry. But anyway, so that's what this thing is the amount of energy released actually from taking this thing from here, from infinity to this position. Okay. It's negative because it's negative work you'd have to do, right? Remember, negative work is the thing moves this way, but the force acting on it is this way. They're in opposite directions, okay? So really what this calculates is the energy you'd need to do to take two masses, M1 and M2, and move them so that they're infinitely far away. Now, V, this is potential. This is gravitational potential. So the gravitational potential is the energy per unit mass, okay? Which is right here, right? So if you multiply a change in potential by a mass, you get energy. So by work, they mean energy, right? So the potential is the the potential energy per unit mass. And that's this guy. Notice this guy's also negative because all we've done is we've divided this guy by one of the masses. So now instead of an actual mass being there, it's hypothetical, right? It's like right here, per unit mass, how much energy does it take to take something from here to infinity? Okay, that's what this guy's answering. And then what this thing is saying is that the gravitational field is the gradient of the potential. Okay, so if you have a uniform gravitational field, it is negative the gradient of the potential, which makes sense, right? Okay, it's like downhill, right? The minus sign means that we're pointing downhill. So that's another way to do this, right? And yeah, there we have it, right? And then we've got a couple other equations here, right? You've got the escape velocity, right? So if we start a distance r from the center of this mass, this is how fast you'd have to go, right? And all they've done is they've got, say, we've got the moon, right? You know, big craters on it, right? Okay, and we start on the surface of the moon. Oh no, can't linger. Okay, we start on the surface of the moon at a distance r from its center. That would be the radius of the moon, and we shoot something straight up. What we're going to say is that it's going to go out here, and when it reaches infinity, it stops moving, right? Of course, when it gets close to infinity, it's going to be almost not moving, right? And so the question is, if we want to shoot it, that's the escape velocity. It's the minimum speed you can shoot something. It doesn't really matter as long as you don't shoot it into the moon. It doesn't matter what direction you shoot it. Okay, to get it so that when it's infinitely far away, it stops moving, right? And so what you're going to say is that here you've got an energy of 1/2 mv squared, where this is the bullet's mass, right? Okay, plus minus this energy here, right? So minus g mass of the moon, mass of the bullet, right? Over r. Notice it's just r, it's not r squared. Okay, just be careful there, right? That's this total energy right here when you shoot it. It's got kinetic, it's got this negative potential energy. And then of course out here, it has zero potential because our denominator here is infinity, right? It's not moving, so it has no kinetic energy, so it's zero, right? So if you solve that, right, obviously I can do some maths here, and I end up with 1/2 v squared is g mass of the moon, right, over r, and then I can multiply this by 2 and get rid of that, and I can square root this, and that's our escape velocity. Okay, and you'll see these, they like to make things on multiple choice tests where you have to like plug stuff into this, yeah. And then this guy down here, that's just our orbital velocity, okay? We can get the orbital velocity, by just setting the centripetal force equal to the gravitational force, right? So gravity, mass of the central body, I'll call that little thing, right? Over r squared is equal to, the little thing is moving around in a circle, right? Right, so here's, big object, that's the Earth or the moon or something that we're orbiting. And we're at a distance. I remember this is not from the surface, it's from the center. Okay. And we're assuming that, by the way, that this object is so big. The big object is much, much bigger than the small object out here, right? The spaceship or the asteroid, or even the moon. We say the moon is much, much smaller than the Earth. We know this isn't true, though, right? The moon is 1/100th the size of the Earth. So the Earth, actually, the water sloshes around it. And that's why we have 2 tides a day. Okay, but anyway, if we solve this guy, the m's go the way of the bison. We lose an r. We have v squared is gm over r. V is going to be just square root of that. So that's our orbital velocity. That's handy, right? I think that's all you have to say about this. So this is just kind of a very poorly organized hodgepodge of formulas. And I wish they would organize it better, but they don't. I see no reason to.